this video, we shall see several examples of normed vector spaces. Let's begin by taking a very basic example. Example 1, R with the inner product AB is just A multiplied by B is an inner product and the associated norm, the norm is the absolute value. No shocker here. This is the simplest and most basic example of an inner product space and the associated norm. Example 2 is something that you have explored in great detail probably in a vector calculus course or multivariable calculus course in your more basic courses. Take Rn and define the inner product of x1 to xn with y1 to yn to be nothing but summation xi yi. You just multiply out the corresponding components and just sum them all from 1 to n. Okay, so this is the standard inner product on Rn. The fact that this is an inner product is rather easy to see, and you can see that the standard norm and metric, Euclidean norm and metric arise from this inner product. These are all easy checks that I am leaving to you. So these are the standard prototype examples of inner product spaces and norms. In fact, these are the prototypes on which the definition, the more abstract definition that we studied, is based on. So let me just make a remark that there are several other natural norms on Rn. Let me just list two of them, and we will sort of explore this in some detail when we come to product metric spaces. You can define the L1 norm, which is denoted like this. This is nothing but the sum of the absolute values of the various components. This is one, and the other one is called the L infinity norm on the Euclidean space, which is denoted like this with an infinity. This is nothing but maximum of the various components. Okay, so needless to say, check that these are norms. Check that these are norms. Now, both of these norms, they do not actually arise from an inner product. I will not show that here. I will maybe put this as an exercise for you. These both do not arise from an inner product. Nevertheless, they are natural and interesting norms, and in some contexts, using these norms will make our lives easier. So we will use these as and when it is appropriate. Now, from the perspective of metric spaces, all these norms are sort of going to be equivalent in a sense that we shall define a bit later. So from our purposes of studying the topology of these spaces, they are all going to be identical. It doesn't matter which one of these norms, whether you put these L1 norm or the L infinity norm, or whether you put the norm that we saw before, the Euclidean norm, it really doesn't matter. All of these are going to be equivalent. Okay, so let's move on to the next example. Example 3. We denote by little l1 all sequences in R such that summation mod xn is less than infinity. Okay, all sequences xn in R such that summation mod xn is less than infinity. In other words, this little L1 is the collection of all sequences whose corresponding series is absolutely convergent. Okay. Now this little L1 is an easy exercise for you to see that this is in fact a vector space with component wise addition, and this definition that we will give you a norm. Okay, so the definition above gives a norm. These are all easy checks that again I'm going to leave it to you. Example 4, this is called little L infinity, and if you have been following the notations that I'm giving, you can sort of guess what this is going to be. This is again going to be all sequences in R that are bounded. Okay, again it's very easy to see that this is going to be a vector space with component wise addition and component wise scalar multiplication. And what you do is, if xn is a sequence that's there in L infinity, we define norm xn to be, as you can guess, maximum of mod xn such that n comes from the natural numbers. You take the highest absolute value quantity in this sequence. So since this is bounded, such a maximum will exist. To be 100% precise, I shouldn't really use maximum, I should use supremum, because it's quite conceivable that this highest value, is not really part of the sequence. For instance, if you can just take the sequence 1 minus 1 by n, the norm of that sequence is actually 1, and 1 is not really an element of this sequence. Okay, so I want you to check the details of these examples. Make sure that you understand why in each case the space under consideration is a vector space and why indeed that it is a norm. Now the example BXR, which we have already seen, example 5 is BXR, which we already saw. Okay, where X is a set, and BXR was nothing but the set of all bounded functions on X. Okay, this is clearly going to be a vector space. This is going to be a vector space under pointwise addition and pointwise scalar multiplication. That's easy to see. This is going to be a vector space, and if you recall, we had defined a sup norm on this space. Let me recall, it was just, if you take a function, the sup norm of the function is supremum mod f of x as x runs through x. This was the norm of a function, bounded function defined on the set S. Okay, now you can check that indeed this satisfies all the properties of a norm, and therefore you get a metric that we have discussed before. Now one interesting thing is, on this space BXR, you can in fact multiply two functions. So as an exercise, I want you to check that norm fg is less than or equal to norm f times norm g, and that inequality need not always be an equality. Think of an explicit example where this is not going to be an equality. Please do this. This is an interesting and basic exercise. Okay, so again I want you to check example 5 also in detail. In some sense, example 5 is the most important example from our perspective. Okay, now let me make a general definition that is going to come again and again in this course and elsewhere in topology. Definition: definition. This is the definition of a subspace. The definition of a subspace. Let X be a metric space. And Y subset of X be a subset. Okay. On Y we can define a metric. This is just D restricted to Y cross Y. You have this function D which is defined on X times X to R. We can restrict it to this product Y cross Y. Then we say Y with the metric. The fact that this is going to be a metric is obvious. With the metric is a subspace. Of X. So this is just, there was no need to actually take out time and highlight this as a definition. Whenever you have a subset of a metric space, you can make it into a metric space in a natural way by taking the metric in the ambient space X and just restricting it to Y. Now we are going to study all sorts of subspaces in this course, but there are many interesting subspaces of just Rn. Okay, so let me just highlight a few interesting subspaces of just Rn. Take Rn or take just R and consider n subset of R. Okay, the natural numbers. Now you can restrict the metric on R to this natural numbers, and you will notice that this, when you restrict it, this space n behaves very similar. So n with this metric behaves in a similar way to n with discrete metric. Now I'm not going to make this precise. What I'm going to ask you to do is to think about this, and can you make this precise? What is the meaning of n with this metric looks very similar to the discrete metric? Can you make a more precise statement? I'm going to leave it to you as an exercise. Now coming back to the general scenario of Rn, there are very important examples of metric spaces, very important examples of metric spaces, metric subspaces. Let me put subspaces of Rn called submanifolds. So rather than spending an elongated amount of time defining what a submanifold is, I will just say they are things like, if you are taking R2, they are nothing but things like circles and parabolas and ellipses. These are things that are smooth curves that are sitting inside R2. Similarly, in higher dimension, all these nice surfaces like spheres and cylinders and the higher dimension analogs of these are all subspaces called submanifolds. Locally they will look like Euclidean space. I'm not going to make this precise in this course. On these you always have a metric coming from the subspace, coming from the ambient metric on Rn. You can put a metric on these submanifolds. Now these submanifolds are very important and they are studied in differential topology and differential geometry. Now oftentimes on these subspaces, the Euclidean metric is not the nicest metric to put on it. I'll just give one example. Look at S1 subset of R. This is S1 is nothing but the unit circle. is nothing but the unit circle. Now we can define another metric on S1 as follows, if x comma y are elements of S1, then dxy is the length of the shortest arc between x and y. There are two arcs on the circle that join x and y. Look at the length of the shorter one. You can spend some time and show that this definition will in fact give you a alternative metric on the circle that is different from the one that comes from the ambient Euclidean space. Now, since we have dealt with subspaces, now when you make statements like, let's say, suppose I say I have this metric space X and I have a subspace Y subset of X. Now if I have a set G subset of Y and I say G is open, suppose I say G is open, then what does this even mean? What does this even mean? This statement G is open could mean two things. Does it mean that G is open in Y, or does it mean that G is open in X? What I mean by that is, do I view G as a subset of Y with the subspace metric, or do I view G as a subspace of X? How do I view it? What does this statement open mean now? Okay. To make this point that this is not a trivial statement, observe that this Y, if I treat it as a metric space in of itself, this Y is always open. Y is always open when I view it in the metric space Y, right? So this is somewhat tricky. It's not always true that if you have G which is open, when you treat it as a subset of Y, it may not be open when you treat it as a subspace of subset of X. It depends on what is the parent metric space we are going to consider. So whenever you have this nested subspaces Y subset of X, so you have potential ambiguity. When we say G is open, we always mean in the parent metric space. That means X. That is X. Okay. So whenever we just make a blanket statement, then you look at the largest metric space that we are considering and it is open in that. That's what it means. Okay. Now if you want to say G considered as a subset of Y and treating it as a whether you want to check whether it's an open set when you treat it as a subset of Y, then we will say G is open in Y. Okay. So if you want to distinguish that we are treating Y as the metric space under which we are analyzing G, we will be explicit and we will say G is open in Y. Similarly, same remarks apply for closed sets. So similar remarks for closed sets. Don't make this mistake of thinking that open and closed are absolute concepts. Open and closed always depend on which metric space we are considering, and for that given situation when there are multiple metric spaces, be very, very careful and think which metric space we are trying to make the statement under. Okay. So in this context, we have this nice exercise. Suppose X is a metric space. Y is a subset of X, is a subspace. So we are treating this subset itself as a metric space with the metric induced by the ambient metric space X. Then a set G subset of Y is open in Y if and only if we can find U subset of X open with G equal to U intersect Y. So intentionally I'm not going to clarify the meanings of the occurrences of the word open. I want you to figure out what each occurrence of the term open, what it actually means. Okay, so with that being said, let's move to the next example. We already considered the space Bxr when X is any set. So now let X be a metric space. There's absolutely nothing stopping us from considering Bxr again, right? Just because X is a metric space doesn't mean that we can't talk about Bxr. X just happens to have more structure than required. So Bxr with this sup norm is of course a metric space. Okay. Now that is not the interesting bit. Consider BCXR. This is bounded and continuous functions. That's one of the advantages of putting X as a metric space. We can talk about continuity, bounded and continuous functions on X. This BCXR is of course a subspace of Bxr. Okay. Not only is it going to be a subspace of Bxr, this is actually complete. Which we will prove soon enough. And this is again one of the most important examples of metric spaces and normed vector spaces. Okay, so let me just make a definition in this context. Definition: a complete metric space is called a Banach space. Okay, an exercise. R is obviously a Banach space. Show that Rn with Euclidean metric is a Banach space. This is a rather important exercise, but not very challenging. Now we are going to generalize this last example a bit further, and this will be the final example of normed vector spaces that we are going to study. Example, I have forgotten what number I am in. Somewhere down the line I stopped putting numbers. Let X be a metric space and Y be a Banach space. So the codomain is no longer real numbers, but it's a Banach space. Okay. Just one moment. I made one mistake here. A complete normed vector space. Normed vector space is called a Banach space. I wrote metric space, but it's actually a normed vector space. What this means is that you look at the metric space coming from the norm, and that metric space should be complete. That's what a complete normed vector space means. Okay, sorry about this. Please make that correction. So now we are in a situation where we have X a metric space and Y is a Banach space. What we are going to consider is Bxy. This is the collection of all bounded functions from X to Y. Because Y is a Banach space, there is a metric, you can talk about a bounded function. This just means that the range of the function is contained in some open ball centered at the origin of the space Y. That's what bounded function means. Okay, so you can check that this is a normed vector space. This is a normed vector space. First check that it's a vector space, and it's also a normed vector space with a sup norm. And the sup norm of a function f is nothing but supremum x in x norm f of x. You take all the possible values of f evaluated at various points of capital X. Because this is bounded, this entire quantity is going to be a finite number. Okay, you can check again that this is going to be a norm. These are all trivial checks. That's why I'm going to leave it to you. Now note that because X is a metric space and Y is a Banach space, therefore Y is also a metric space, we can also talk about continuous functions from X to Y. You can also talk about the space of continuous functions from X to Y, but because X is just a general metric space, we will later study compactness. If X is compact, then this is also going to be a normed vector space. It's also going to be a normed vector space with sup norm. In fact, it's going to be a subspace of Bxy, because continuous functions on compact sets will turn out to be bounded, just as we have seen for the real numbers. However, if X is just a general metric space, there is no reason to believe that a continuous function is going to be bounded. So because of that, we have to consider BCxy. Again, BCxy. This is just Cxy intersect Bxy. And exactly as before, we will see that this is also complete. Okay. Later, towards the end of these set of videos on metric spaces, we will study the compact subsets. Of this BCxy. Okay, that is the famous Ascoli-Arzelà theorem. So with this collection of examples of normed vector spaces, I leave you with a lot of minor details to check. I urge you to do it at least once in your life, because these details might seem irrelevant to you, but trust me and take it from me that it is important that you check it once. This is a course on real analysis, and you have just watched the video on examples of normed vector spaces.